let's say we had this truss system over here, and we had a force F applied at this point over here. Okay, and let's say that this point displaces down by distance delta. We can quantify the amount of energy that this force exerts onto the system by the external work done. So the external work is equal to a half times the force times the distance. I'm not really sure where the half comes from, but we move. And then, so this is the external work, right, that the force exerts onto the system, right? Internally, the truss itself is going to deform and deflect and store all of that energy that was exerted onto it as potential energy, right? So if you model each of these members, right, if you model them as springs, right, they're going to deflect and deform, and they're going to store potential energy, right? And we can model them as springs because we're working in the linear elastic region, right? None of these are plastically deforming. So that's our assumption for the problem. So cool, if we know that, then we could probably calculate the deflection of each and every member. And let's say we wanted to calculate the deflection of this point over here. If we wanted to calculate the deflection of this point, we'd need to see, we could probably evaluate it geometrically, but we'd need to see how this member deflects, how that member deflects, and how that member deflects. So if we know that, okay, this member deflects down by so much, this one deflects to the right by so much, and this one also deflects to the right by so much, eventually the point would end up somewhere here. So it will translate something like that, for example, right? You can see that trying to do that is very tedious, and very difficult. So what we do instead, we create a virtual system, right? So we use the basic principle that the external work is going to be equal to the amount of internal energy that this truss system has. So for our virtual system, what we do is we draw a force. This force can have any value. So we draw a force at the point where we want to evaluate its displacement. Okay, the force can have any value, and then the premise is that the deflection of the original system and the virtual system are going to be exactly the same, right? So what we do is we say, okay, this force is going to exert a certain amount of energy, so it's going to do work. So again, we use this equation over here, and we're just going to change this F to our virtual force. And then we want to calculate this deflection. Then we said that it's equal to the internal energy stored inside the system. So we're going to write the internal energy, right, in terms of the normal forces of each of the members. So each of the normal forces in these members do some work, right? So the normal force in this member is going to stretch the member somehow, and that's basically doing work on the member. The normal force in this member is doing work by stretching it by some distance, right? So cool, we can write that as Ni, which is the normal force of all the members of each member in our virtual system, multiplied by, I'm going to call it delta I, which is the deflection of the normal force in each member. We can equate these two equations together, then we'll get a half Fv times delta, which is equal to the sum of Ni times delta I. The problem now is that if we wanted to use this equation as is, we would have to calculate the deflection for each and every single member, which isn't feasible, right? So what we can do, since we said that the deflection of each and every, for the deflection for the virtual system and the original system is the same, we can rewrite this deflection, right? Since we're modeling everything as a spring, we can go back to our original system and say that, we can say that the normal force in each member is equal to the stiffness of the member times the deflection of the member, right? Cool. So we know how to calculate the normal force in each member, and the stiffness of each member for a 1D bar, if I'm not mistaken, it's EA over L, right? So the elastic modulus of each member multiplied by the area of each member divided by its length, right? And then we can rewrite this equation in terms of delta, and we can say it's equal to Ni over Ki, which then gives us Ni Li over Ei Ai. And then we substitute this back into this equation, right? So we get the following. Sorry, this is supposed to be a half. My bad. So we get a half sum of Ni, again Ni Li over Ei Ai. Okay, cool. So just to recap, this is your virtual force. It can be any value whatsoever. So as you change the virtual force, you're going to change the internal force at each member of the virtual system, right? So these two are interconnected within this equation, right? And the displacements remain the same, right? Because the displacement of the original system is the same as the displacement of the virtual system. The only thing that's changing is that this displacement now is the displacement at a particular point, right? Okay, so as long as you change this, it changes that. So then the equation balances itself out in some way. So yeah, hopefully that makes sense. And then the way in which you would actually use this formula, you would place your force, you would place your virtual force, you would choose a value for it. You could choose literally 1 Newton, and then afterwards the next thing we need is the internal force for each and every member of the virtual system and each and every member of our original system. So you would basically draw your free body diagrams, calculate the internal forces for each of the members, and then once you're done with that, you basically just fill out this entire equation, right? So yeah, hopefully that makes sense.